Hello, math friends. Today we are going to start Chapter 4. Chapter 4 is on exponents and logs. So our first section, section 4.1, deals with exponential functions. The standard form of an exponential function looks like f of x equals c times a to the x minus h power plus k. And we have a few rules here. Our a value must be greater than 0, and also a does not equal 1, because if a equals 1, we would not see any exponential growth because the base of the exponential part of our function would be 1. 1 to any power is always 1. The parent graph of this, without any shifts, is just f of x equals a to the x power. The characteristics, again, a must be greater than 0, a cannot equal 1, kind of repeated from above. We have a horizontal asymptote at y equals 0. The domain of every exponential function is all reals. Your range is going to be y is greater than 0, or if we wrote it in interval form, from 0 to infinity. So on the graph here, we're going to graph two different functions, y equals 2 to the x power and y equals 1/2 to the x power, so we can kind of compare and contrast. So 2 to the x power, if we just kind of make a little table, and again, you don't even have to write this down, but this just kind of gives you an idea of what's going on as you plot your points. We can choose our kind of fave 5 here, -2, -1, 0, 1, and 2 for our x values. And when we plug these into the function, 2 to the -2 power, remember a negative exponent brings it downstairs, so that is 1 over 2 squared, or 1/4. 2 to the -1 power would be 1 over 2 to the first, or 1/2. Anything to the 0 power is 1, so 2 to the 0 power is 1, 2 to the first power is 2, and 2 squared is 4. So we go ahead and plot these points. -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. And this is the graph of y equals 2 to the x power. Then on the other side here, I'm going to graph y equals 1/2 x, 1/2 to the x, excuse me. So again, it's not necessary to make a table if you know what the function looks like, but if you need to, please feel free. I'm going to choose the same 5 x values, but when I plug them in, 1/2 to the -2, remember that flips things over, and that becomes 2 to the first power, or sorry, 2 to the second power, which is 4. And then 1/2 to the -1 becomes 2 over 1 to the +1, which is just 2. Anything to the 0 power is 1, so 1/2 to the 0 power is 1. 1/2 to the first power is 1/2, and 1/2 squared is 1/4. So now when x is -2, y is 4. When x is -1, y is 2. When x is 0, y is 1. When x is 1, y is 1/2. And when x is 2, y is 1/4. And this is our graph of y equals 1/2 to the x power. So now you can kind of compare. You can see that these are mirror images of each other over the line, or over the y-axis. On the next screen, we're going to graph each of the following by transforming our parent graph. So when we look at the first function, y equals -2 to the x power, I'm going to rewrite this as -1 times 2 to the x. Okay, we're still going to have an asymptote at y equals 0. The only time that changes is if we have a vertical shift. So if you wanted to put a little note here, this depends on if we have a k value. That's the only time our asymptote is going to move. Otherwise, it's always going to be at 0. And I have this little note here that -1 is an a value, which we're familiar with a values, right? And if a is -1, that flips the graph over the x-axis. So if we think about what our parent graph looked like in the previous example, we had 2 to the x graphed. So I'm going to go ahead and I'm just going to kind of put the dots there. I'm not going to connect them, but those were the dots for our function. So now if the only thing we're doing is adding that reflection over our x-axis, then I can go ahead and I can just reflect these points right over the x-axis. And I can graph my function. My domain here is still all reals. My range now, because I had that x-axis reflection, my range is going to be that y is less than 0, or in interval notation, -infinity up to 0, round brackets on both. In the second example, I've got 2 to the x power plus 2. Okay, so now this is going to change things. I'm going to do my note first here. My k is a +2, so this is going to shift the parent graph up 2. And since I'm moving the whole parent up 2, this changes my asymptote. So this is going to put my asymptote now at +2 instead of at 0. So I'm actually going to go and backtrack here for a second, and I'm going to sketch in my asymptotes real quick, just so we can see those. Now my parent graph, again, if I plot those points, same points that I was plotting before, right there. Okay, but now for my graph, I'm going to be shifting them up 2. So that is what the graph of y equals 2 to the x power plus 2 is going to look like. My domain, always all reals for exponential functions. That never changes. My range now changes, though, because I shifted my graph up 2. So obviously a vertical shift is going to affect where my graph lives along the y-axis. My range is now that all my y values are greater than 2, or in interval notation from 2 to infinity. In the next example, we have another shift. Okay, again, our parent graph is still y equals 2 to the x, but this time we have an h value. And if we see x minus 3, remember that means that h is actually +3. So this is going to shift our parent points 3 to the right because h is +3. Since we're not changing our y values, we're not changing our asymptote, we're still going to have a horizontal asymptote at y equals 0. So I'm going to go ahead and sketch that in right away. And I know what my parent points look like, so I'm quickly just going to sketch those in. There they are. Okay, but now if I'm shifting all of my points 3 units to the right, my final graph is going to look like that. Okay. And if you want to put a little note here, just so that you don't forget, the horizontal asymptote does not change for horizontal shifts, right? We had that previous example where we had the vertical shift and that changed our horizontal asymptote. So just really trying to emphasize that the horizontal asymptote is affected by our k values. Our domain here It's an exponential function, so x is all reals. Our range, since we did not change our asymptote, is going to be y is greater than 0 or the interval 0 to infinity. So this has just kind of been a review of what an exponential function looks like and the different shifts that we can have that can move it left, right, up, down. And of course, when we have our vertical shifts, we're affecting our horizontal asymptote. Now we're going to transition to a different base. Okay, and this again is review from Algebra 2. Our parent graph for the natural exponential function is going to be f of x equals e to the x, where e is our base. And remember, e is a number. It's irrational. We approximate it to about 2.72 or 2.71, excuse me. Okay, so we'll put that under our characteristics, that e is approximately equal to 2.71828 ... So 2.72 is usually about what we approximate it as. Since this is an exponential function, it just has a base of 2.7. We're still going to have our horizontal asymptote at y equals 0. Our domain is still going to be all reals, and our range is still going to be that y is greater than 0 or from 0 to infinity, because we're not changing anything if we're just graphing our parent function. I'm going to make a little table here for y equals e to the x, just because these are some values that you probably want to type into your calculator. And I'm going to do my fave 5, -2, -1, 0, 1, and 2. And these values are going to be the same for every parent graph of y equals e to the x. When our exponent is -2, e to the -2 power gives us approximately 0.1. E to the -1 power is 0.4. E to the 0 is 1, because anything to the 0 power is 1. E to the first power is just the value of e, so about 2.7, and e squared is about 7.4. So now I'm going to go ahead and plot these points: -2.1, -1.4, 0, 1, 1, 2.7, and then 2, 7.4 is way up there. So this one climbs a little bit faster than the graphs that we were plotting previously. The next thing we're going to do is just practice using our calculator. This isn't hard at all. You don't need a graphing calculator to do this. Any calculator will do these functions. We're just going to practice evaluating e to a power on the calculator. So first, locate your e button. Most of the time it's somewhere near your ln or your natural log. A lot of times it's a second level function above your ln key. So we'll just type in e to the 4th. On my calculator, I would go e caret 4, and you should get as your answer 54.60. Second one here, 2 times e to the -0.37 power. So on my calculator, I'm going to type 2 times e caret, and then I'm going to use parentheses just to make sure there are no computational order of operations errors here. -0.37 is what I'm raising it to. I hit enter. You should get 1.38. And then my last example, this one's a little tricky to plug in, so we have to make sure that we're plugging everything in accurately. I'm going to have -5. I'm multiplying it times the radical, so times. Then on my calculator, I hit square root. Since everything is under the square root, now I have to use a parenthesis, and it's going to be 3 times e caret 2. And when I hit enter, you should get -23.54. So just take a moment, please, and practice using your calculator so that you're comfortable with that E button and that function on your calculator.